Hello students, welcome to the Genesis Questions classes, Bazar, Guwahati. I am here to teach about the physics classes, and we start today with a small topics, electric charge. I hope all of you know about the electric charge. Basically, there are two types of electric charges. One is positive charge, another is negative charge. And we all know that the magnitude of charge equals to 1.6 into 10 to the power minus 19 coulomb. This one for positive and this one for negative. Positive means proton. Proton is a positive charge, and negative means electron. Electron is a negative charge, but both the two charges have the same magnitude, 1.6 into 10 to the minus 19 coulomb. Okay, now let's move to the basic properties of electric charges. What are the basic properties of electric charges? See, basic properties. Number one, additivity of charges. Number two, quantization of charges. And last one, number three, is the conservation of charges. So what is additivity of charges? So this property means if we have a system of charges, suppose Q1, Q2, Q3 up to Qn, that means n number of charges. A system consists of n number of charges. Then according to this property, the total charge of the system is equals to Q1 plus Q2 plus Q3 plus up to Qn. So this is about additivity of charges. So if a system consists of n number of charges, means Q1, Q2, Q3 up to Qn, then the total charge of the system is always equals to Q1 plus Q2 plus Q3 plus up to Qn. That means addition of the charges. Suppose, for an example, we consider a system of charges which consists 5 number of charges. 5 number of charges. 1 coulomb. Suppose 1 microcoulomb. Small charge. 2 microcoulomb. 3 microcoulomb. Minus 4 microcoulomb. And last one, 5 microcoulomb. Then the total charge of the system is equals to 1 plus, there is a plus 2, so plus 2 plus 3, but 4 microcoulomb is a negative charge, so minus 4, and last one again positive charge, so plus 5. So total charge equals to 5, 6, 11 minus 4, that means 7 microcoulomb. The second property is quantization of charges. Now, according to this property, the charge Q equals to integral multiple of basic quanta of charge. That means here n equals to 0, plus minus 1, plus minus 2, plus minus 3. So according to this property, the total charges of a system, of a body, or of a matter is always equals to integral multiple of basic quantum of charge. This one, small e, basic quantum charge, which is equals to 1.6 into 10 to the minus 19 coulomb. That means when charges are produced, again, how charges are produced? By using the process of rubbing. Suppose this is the plastic, when we rub this plastic with a woolen cloth, then this plastic appears a charge, appears a negative charge. So during rubbing, suppose this is our plastic, suppose this is our woolen cloth. So while rubbing, the charges flow from woolen cloth to plastic according to this property. That means according to the quantization of charge. So first, when we rubbing, then the charge starts flow from woolen to plastic. First 1 number, next 2, next 3. That means it moves discontinuous or discrete amount of charges. The flow of charge is not continuous. The flow of charge is discontinuous. The flow of charge is discontinuous. Okay, that means first number of charge. Secondly, second number of charge flows from woolen to plastic. Then third one, and so on. Okay, so this is about the quantization of charge. So main point is, according to this quantization of charge, the charge or total charge is always equal to the integral multiple of basic quantum of charge. Okay, now move to the last property, conservation of charges. The last property is conservation of charges. Our last property is number 3, conservation of charges. This property is similar to the law of conservation of energy. That means the total charge of a system Q is always conserved. That means always constant. So according to this property, the charge of a system neither be created nor be destroyed. It can only transfer from one system to other or one body to other. That means charge always transferred from one body to other. It cannot be destroyed, or it neither be destroyed nor be created. Okay, these are the 3 basic properties of electric charges. Now move to the electrostatic forces between 2 charges. Electrostatic forces between 2 charges. Electrostatic forces between 2 point charges, suppose. Let's consider 2 charges. Suppose at point A there is charge Q1 and at point B there is another charge Q2, and these 2 charges are separated by a distance R. So the force between these 2 charges is governed by Coulomb's law. So according to Coulomb's law, the force between 2 charges A and B, or Q1 and Q2, is directly proportional to the product of the magnitude of the 2 charges. That means force between 2 charges is directly proportional to Q1 and Q2. And one more point, according to Coulomb's law, this force also inversely proportional to the square of the distance between the 2 charges. That means 1 by R square. Now combining these 2 points, we will get F proportion to Q1 Q2 by R square, or F equals to, there is a constant, suppose K, Q1 Q2 by R square. Now this constant K is equals to 1 by 4 pi epsilon naught for the medium. Medium means the medium between Q1 and Q2 is air. And here epsilon naught is the permittivity. Of free space. So we'll get the final formula of force F equals to 1 by 4 pi epsilon naught Q1 Q2 by R square. This is the electrostatic force between the two charges according to the Coulomb's law. So we will get the formula for electrostatic force between two charges is F equals to 1 by 4 pi epsilon naught Q1 Q2 by R square. Here the epsilon naught is the permittivity of free space, and the value of epsilon naught for free space equals to 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square, and 1 by 4 pi epsilon naught equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. So these are the standard values. One is epsilon naught and other is the whole constant 1 by 4 pi epsilon naught, which is equals to 9 into 10 to the power 9 Newton meter square per Coulomb square. Now try to solve a problem related to the electrostatic force. So see, there is a question. I think this question is Neet 2019. Also 2019, yes. So the question is, the two surges plus Q and minus Q are placed at points A and B respectively at a certain distance, and force between the two surges is F. That means initially the force between the two surges is F. This is given. Now the question is, if 25% of charge 25% of charge is transferred from A to B, that means 25% of plus Q charge is transferred to minus Q, then the force becomes option 1 F, option 2 2F, option 3 9 by 16F, and option 4 last one 16 by 9F. So let's try to solve this. There are two surges, this one at A point plus Q, and another surge at point B minus Q. So for first case, that means initial case, for this one, the force F equals to 1 by 4 pi epsilon naught Q into Q divided by, suppose distance is R, so R square. Why Q into Q? Because the magnitude of the two surges are same. One is plus Q and other is minus Q. So F equals to 1 by 4 pi epsilon naught Q square by R square. First equation from the first condition. Now move to the second condition. The second condition is, if the 25% of charge is transferred from A to B, (25% of charge A), that means 25% of plus Q charge is transferred to charge B. So new surge at A, QA equals to Q minus 25%, means 1 by 4th. 25% means 1 by 4th of the original surge, and the original surge is Q, so minus Q by 4. And the other charge at B equals to Q plus Q by 4. Originally here charge is minus Q. Originally the charge at B is minus Q, so minus Q. So new charge of A equals to 3Q by 4, and new charge of B is minus 3Q by 4. So the force F equals to 1 by 4 pi epsilon naught 3Q by 4 into 3Q by 4, again the magnitudes are same, 3Q by 4 divided by distance is same, R, divided by R square. Now try to solve this one. This one f dash, say f dash equals to 1 by 4 pi epsilon naught. This one 9 by 16 into q square by r square, or f dash equals to 9 by 16 into 1 by 4 pi epsilon naught q square by r square. Now compare this with equation number 1. So from equation number 1, 1 by 4 by epsilon naught q square by r square equals to f. So we'll get the final answer, f dash equals to 9 by 16 f. That means option 3 is correct. F dash equals to 9 by 16 into f. The next question is, see, two identical charges are kept suspended by two massless string of negligible mass of length L, and the two charges are initially at a separation of d due to force of repulsion. First, this is the first given condition. Now the second point is, the charges are begin to leak with a constant rate, due to which the two charges approaches each other with velocity v. The velocity v varies as a function of distance x is number A v proportion to x square, number b v proportion to x to the power minus 1, number c v proportion to x to the power minus half, and number d v proportion to x to the power half. Now let's try to solve this. First, the two charges are suspended by two massless string, each of length small l. Suppose this one first charge and this one second, and the length of the string is small l. Let the separation between the two charges after discharging is small x. This one given in the question small x. So if from A to B is x, then this will be the midpoint O. So from A to O, this will be x by 2, and from O to B, this one x by 2. Let this angle is theta. Now, due to the mass of the surge, there is a tension in the string T, and the weight of the charge is always acting vertically downward direction, and weight is always equals to mg. Now, if this angle is theta, then according to the geometry, this angle is also theta. If this one is theta, then along this direction there is a component of tension T cos theta, and along this direction, this one x by 2, along this direction the another component of T is T sin theta. Fine. Now, since according to the question the two surges are identical, that means nature of the two surges are same, so there is a force of repulsion. Say at this point the repulsive force acting along this direction, and the repulsive force equals to constant, which is equals to 1 by 4 pi epsilon naught, and the value of k is equals to 9 into 10 to the power 9. So k into q square divided by x square. Now see, in this figure, according to the geometry, this component is balanced by this force, and this component is balanced by this weight. That means in equilibrium condition we will write T cos theta equals to mg, equation number 1, and T sin theta equals to this force K q square by x square, equation number 2. Now dividing equation 2 by 1, we'll get t sin theta by t cos theta in the left hand side, and in the right hand side we'll get k q square by x square into mg. This t is this cancel. Now sin theta by cos theta equals to tan theta, and tan theta equals to this one k q square by mg into 1 by x square. Fine. Now again, from the figure here, theta is a very small angle. Theta is a very small angle. So if theta is a very small, then we'll write theta is almost equals to tan theta. Theta is almost equals to sin theta. Okay, that means tan theta equals to theta, which is equals to k into q square by mg into 1 by x square. Now again, from figure, suppose this one A point, this one O point, and this one suppose C point. So from triangle AOC, from this triangle, if we apply sin theta here, sin theta, then sin theta equals to, the formula for sin theta is perpendicular by hypotenuse. So perpendicular means from A to O, hypotenuse means from A to C. So sin theta equals to from A to O, and its hypotenuse equals to from A to C. Again, sin theta is almost equals to theta, and from A to O, this one x by 2. X by 2, and from A to C, that means length of the string which is given in the question L, then we will get theta equals to x by 2L. Now comparing these two equations, here theta equals to k q square by mg into 1 by x square, and theta equals to x by 2L, we will get x by 2L equals to k constant q square by mg into 1 by x square, or x cube equals to k q square by mg into twice L, or x cube equals to 2k q square by mg into L. Now from this equation we'll get q square equals to mg by 2k L into x cube, or only q equals to root over mg by 2k L x to the power 3 by 2. Equation number suppose 1. Now according to the question, the charges begin to leak with a constant rate. That means the rate dq by dt is constant. The rate dq by dt equals to constant. Now differentiate equation 1 with respect to time. Now from equation 1, dq by dt equals to this is constant term. So mg by 2kl and x is a variable. Here x is the variable, so ddt of x to the power 3 by 2. Now try to solve it. Or mg by 2kl into इसका डेरिवेटिव कितना होगा 3 by 2 x to the power minus of dx by dt, x to the power plus of dx by dt, or dq by dt equals to dq by dt equals to root over mg divided by 2kl into 3 by 2 x to the power half. This one dx by dt means rate of change of displacement, which is equals to velocity. So dx by dt equals to v. Since dx by dt equals to v, velocity of the charges, two charges, with which the two charges approaches with each other. Now applying the given condition dq by dt equals to constant, we'll get constant equals to root over mg by 2kl into 3 by 2 into x to the power half into v. And suppose this constant equals to capital A. Suppose a equals to root over mg by 2kl into 3 by 2 x to the power half into v. Now v equals to velocity equals to constant a into root over 2kl by mg into 2 by 3 into 1 by x to the power half. Now see this equation. Here the whole term a into root over 2kl by mg into 2 by 3 is a constant. So finally we get v proportion to 1 by x to the power half, or v proportion to x to the power minus half. So this will be the correct option, since this is a constant term. The whole term is a constant. Okay, got it?